Hey, Algebra 2 friends, here we are in section 9.4 of chapter 9, and we're going to be talking about direct, joint, and inverse variation. And that leads us directly to our vocabulary. So direct variation, let me highlight some things real quick so you guys can get an idea of where we're going. So these are the three main topics that we'll talk about today. And we'll talk about constant of variation, but constant of variation is going to be, we're going to have a constant of variation in each of these equations. So what's going to happen is we're basically going to be talking about a relationship between variables. So quickly, direct variation is y equals k times x. So in this case, I'd say y varies directly as x. Don't worry to copy this now. I'm going to say all of this again. And then joint variation is when y varies directly with k, x, and maybe some other variable z. I could even throw a w in there. That's the relationship. So y varies jointly with x and z in this situation. And then over here, y varies inversely with x, and this one can also be written as y times x is equal to k. And so basically what you have to do is memorize these situations. So you're like, okay, lady, you still didn't tell us what the constant of variation is. Well, in each of these cases, the constant of variation is k. And what k refers to is some non-zero number that maintains this relationship between all the y and x values, or the y, x, and z, whatever values that you're dealing with. Okay, let's look at this a little bit extensively. So here it is written out. Let me see if I can make sure you guys are seeing all of it. There we go. Widen the lens there. Okay, so these are key concepts. They're found in your textbook, and they're literally, I just rewrote this. But if you want to take some time now, I'm going to read over it again just to make sure we have it. So if you might be given a problem like with direct variation where you say y varies directly as x, and you might see that y is equal to 10 when x is equal to 3. And then the question will be, what is y in this situation when x is equal to 7? Okay, so this is the type of problem that you're going to be answering. And then so you remember, if it's a direct variation, that means that 10y is equal to some number k times 3, right? So what would k be? You can solve this and you would say, oh, in this particular relationship, k is 10 over 3. You guys see how I did that? Divided both sides by 3. So you would take this 10 over 3 and you'd use it in this relationship here. So we're looking for y when x is 7. We remember y equals k times x. Therefore, y equals 10 over 3 times x, which is 7, and that gives me 70 over 3 or whatever. So in this case, y is equal to 70 over 3 when x is equal to 7. So we're going to take the constant of variation from one relationship and use it in another relationship with those same variables. And we're going to do that for each of these guys, okay? So I'm not going to bore you with trying to show you examples of each of these because we're about to do examples of each of these. So again, as we said, varies jointly. It's kind of like a direct variation, but this time instead of y varying just with one x, it's varying with an x and a z, and k has that relationship. And then the inverse variation is x times y equals k, or y equals k over x. I know you guys have been watching these videos for a long time. I would pause it and try and see if I could answer this question. Just pause it. We just did a direct variation problem. Pause it, see if you can answer it. So I get negative 64. If you got negative 64, I think you can skip this. And if you didn't, then let's work the problem out together. So you remember y is equal to k times x. That's direct variation. How else can we arrange this to represent the same situation? If I were to divide both sides by x, notice what happens. I get y over x is equal to k. This can be very handy in handling direct variation problems. Let's try it this way. So here's what's happening. If I take the relationship that they've given me and I recognize that when y is equal to 12, so I'm going to put 12 over negative 3, this is my k value, I should get the same exact k value when I deal with this unknown y and 16, that known x. So I'm going to put the y over 16 because both of them would represent the same k. And what we have here is a proportion. We know how to solve proportions. We cross multiply and handle business. What I'm going to do here, though, before I do that, is I'm going to simplify this. So this is going to actually simplify to 4 over negative 1 if I divide top and bottom by 3. So now I have 4 over negative 1 is equal to y over 16. When I cross multiply, I think you guys see it, I'm going to end up with 64 is equal to negative y, and therefore y is equal to negative 64. Let's take a look at example 2 and joint variation. I like to write down what I know. So I remember that joint variation was y is equal to k times some other variable, sometimes an x and a z or w or whatever. Let's see what we've got. So I'm going to hold on to this concept and let's read the problem together. So over here, suppose y varies jointly as x and z. So y equals k times xz. Find y when x is equal to 8 and z is equal to 3. So that's the problem. I'm going to write that down, looking for y in this situation. And then they give me the key to the problem because they say, hey, guess what? Y is 16 when x is equal to 5 and z is equal to 2. So I'm going to use that to find my k value. So if the case is that 16 is equal to k times 10, that means that k is equal to 16 over 10. And I can reduce that, obviously, to get something a little bit easier to deal with, which would be 8/5. And I'm going to keep that k value just like that. I'm going to use that k value in order to solve for this y value over here. So watch. Y is equal to 8 over 5 times 8 times 3. And this is just a matter of multiplication. So I'm going to get my 64 times 3 and I'm going to divide that by 5. And when I'm done, is that y is equal to 38 and 2/5. Here we are in example 3 and we're going to use inverse variation. So we remember inverse variation has some kind of situation where one variable y is equal to k over x, or sometimes we look at it as x times y is equal to k. Let's see how this works out. So if r varies inversely as t, that means r is equal to some k value divided by t, or rt is equal to some constant k, and r is equal to 18 when t is equal to negative 3, find r when t is equal to negative 11. All right, so here's how I like to do this problem. And I know the text does it in a different way, but in both of these RT situations, R times T has to equal K, right? Because that's what the constant of variation is within an inverse variation situation. I said a lot of stuff. So here's what I want us to do. I want us to take the R and T, the known R and T, that's 18 times that negative 3, recognize that it is equal to K, but also this one over here, this t equaling negative 11 and this mysterious r is also going to multiply to give me k. Why do I need to find k when I really want to find r? So I won't. What I'll do is say 18 times negative 3 is equal to negative 11r, and I'm going to solve this equation instead. So what I'll do is I'll multiply 18 times 3. Can I do that? I think I can. So I get 4 carrier 2, 3 times 1, 3, 4, 5. So I'm going to get 54. Negative 54 is equal to negative 11r. Divide both sides by negative 11. And then I get that r in this case is equal to negative 4 and 10 elevenths. Yeah, negative 4 and 10 elevenths. I think you guys saw my mistake. It is a positive because the negatives canceled each other out. So positive 4 and 10 elevenths. Okay, let's move on to the last example. Okay, so here's our final example. Then I won't lie, I wanted to skip because it was a little bit weird and a little unwieldy for me to get at first. And then I looked at it and I was like, okay, I get it. But I think my friends want to know about it, so I owe it to them to explain. So let's see if I can do a decent job. The apparent length of an object is inversely proportional to one's distance from the object. We find out that Earth is 93 million miles from the sun. We're going to use the information at the left to find out how much larger the diameter of the sun would appear on a Mercury than it would on Earth. And I don't know why that's taken me a long time to figure out, but it's just a lot of gobbledygook. So here's what I think. I think drawing a diagram is helpful. So I'm going to start off by just having the sun, and here's my Earth that's 93 miles away. And then the other bit that we need to know is find out about the distance from Mercury to the sun, and that is given in this little side information that that's about 36 miles. And I know that my drawing is not drawn to scale, so that's 36 million miles rather. And so what we need to do is consider this relationship. So what we have is that there's an inverse proportionality to the way that the like a person, I know this is getting so crazy, but a person standing in, nobody can stand on Mercury, it's too hot, but a person standing on Mercury would see the sun as really huge even though its distance is small, whereas a person standing on Earth would see it as smaller because the distance is greater, right? So that's where the inverse relationship comes from. So let's write that down mathematically. So the first relationship I want to explore mathematically is the one of Earth and the sun. Since we're comparing the distance or the view from Mercury to that of Earth, let us call the view in terms of what the sun looks like as some unit length of 1. Therefore, 1 is equal to k over 93, right? As some value y is equal to that same k value over 36. And this y value, when we figure out what y is, that's how we're going to calculate how much more, how much larger the sun would appear if you were standing on Mercury. So remember we talked about the fact that k is the same in both of these situations. Therefore, 93 times 1 has to equal to 36 times y. You guys see a pretty easy equation that we're about to solve. You got it. We're going to divide both sides by 36, and we'll have that y is equal to 93 over 36. And let me, I think we can do this without a calculator. But why bother? Let's use a calculator and get 2.583. Repeating, it looks like another 5. So approximately, if we round to the nearest hundredth, 2.58 times larger it would appear on Mercury than on Earth. I hope that made sense, and I hope that you can see how to use direct variation and joint variation and inverse variation with the problems that you have for your assignment. Also, though, the textbook chooses to do it a different way. If you're not like vibing the way that I'm doing it, feel free to look at the textbook and see if you like that way. I felt like they were asking us to memorize more. So I was like, I don't want to memorize more. Let's just memorize the forms. But go ahead and check it out. Let me know. We can chat about it when we see each other later. Guys, have an excellent day. I look forward to talking to you soon. Bye-bye.